So we start to move into chapter 12. I think this is 12.3, simplifying radicals. Um, Again, in working with radicals, there are different types of radicals. Again, this symbol here serves two purposes. Let me see if I can get that to show again. So this is called the radical symbol, but this is also called the square root symbol. So it kind of has two purposes. There used to be like a little number here, little 2, index number of 2, but over time, the 2 got taken away. So this radical symbol also serves as the square root symbol. Now, if I have this symbol here, this is the radical symbol, but if I do this, this now becomes the cube root. And I could continue doing that on and on and on. So this is the radical symbol, but if I put a 4 there, this is now called the fourth root. So what we're working with are what we call square roots. So square roots are the inverses of squaring. So notice that square root is the inverse operation to square a number. So like if I give you 3 squared is 9. But if I go the other direction, the inverse of squaring is what's called the square root. So this symbol here is used. The square root of 9 is going to give me back to what squared actually gave me the 9, which would be the 3. So when we talk about perfect squares, a perfect square is when you pick a number and square it. So notice that 9 would be called a perfect square because 3 squared is 9. So it's pretty easy to take the square root of perfect squares. So if I gave you 4 squared, that's going to equal 16. So 16 is called a perfect square. And the square root of 16, well, what squared gave me 16 was 4. So those are what we call our perfect squares. So if I gave you 12 squared, we know 12 squared is 144, which means if I go the other direction, the square root of 144, since 144 is a perfect square, that's going to give me 12. So those are actually pretty easy to deal with. So one of the things we pick up on is this is a pattern. If we have 2 of the same factor inside the square root, so notice that the square root of 9 has a 3 and a 3 inside of it. So what we pick up on is a perfect square has the same factor twice, and that's going to equal then 3. So those are equivalent. So it's pretty easy to take the square root of perfect squares. Now, if the number is not a perfect square, when taking the square root, the answer is going to be represented by what we call an irrational number. It can be left in what we call simplified radical form. A calculator is often used to convert it to a decimal and round as necessary. So for instance, if I pull out my calculator here, if I take the square root, notice how x squared is the squaring button. So if I do like 7 squared, that's going to give me 49. But right above the square button is the square root symbol. So if I hit the second button and hit the x squared button, the square root of 49 is going to give me back to the 7. So 49 is a perfect square. Since it's got 2 7s in it, it's a perfect square. Therefore, I can take the square root of it, and it's going to take me back to the 7. Now, on the other hand, though, if I give you the square root of 6, notice that 6 is not a perfect square because you can't compose 6 of the same 2 factors. So that's what we call an irrational number. So the square root of 6 is described as, it's going to be described as irrational. So when it's irrational, we can leave it in a simplified radical form. Now, if I want to, I can hit the calculator and it would give me an estimation of what squared would give me 6. So if I square 2.49999, so if I have that answer there, if I square that answer, notice how it's going to take me back to the 6. So, but a lot of times we'll round this. We won't carry it all the way out. So a lot of times if I say round up to the third place, 2.449. So the square root of 6 is approximately 2.449. Now, if I square that, notice that I'm going to get close to 6, not 6. So what happens is we're going to get into what's called simplifying square roots. So simplifying square roots means we're not going to use a calculator per se, is we're going to simplify what's called the radical. And the way we do this is we can use what's called the prime factorization can be used. So what we can do is identify some perfect squares by pairing up common factors and bring those answers outside the radical. So the non-perfect squares are multiplied back together and left inside the radical. So for instance, if I gave you the square root of 45, notice that the prime numbers are 2, 3, 5, 7, 11, sometimes 13. If I use these prime numbers, I could break this 45 down. Well, since 45 is not even, I know 2 is not going to go into that, but 3 does. So 3 does go into 45. And again, you can use a calculator if you wanted to. 3 goes into 45 15 times. So if I want to make a little chart to kind of organize this, put the 45 on top, and 3 goes into 45 15 times. So 3 times 15 gives me 45. But notice that 15 is not prime because 3 does go into 15. So 3 goes into 15 5 times. But notice that 5 is prime. 5 does go into 5 1 time. So what I can do is I can break 45 down into 3 times 3 times 5. Notice that 3 times 3 represents a perfect square. So since this is a perfect square, that comes out as a single factor as a 3. So I can write that as 3 radical 5. So that's called simplifying a radical. So if I come back up to this problem and I'm asked to add and subtract this problem. So if we have 2 square root of 45, if we have 2 square root of 45 minus the square root of 5, we kind of treat this like terms. To have like terms, we have to have like radicals. To have like radicals, what's inside the radical has to be the same. Well, since these are not like radicals, it cannot be simplified. But the square root of 45 can be simplified. So notice that if we simplify the square root of 45, notice how there's already a 2 here. This could turn into 2 times then, and the square root of 45 could change into 3 times 3 times 5 minus the square root of 5. Notice that these two 3's can be brought on the outside. So this is actually going to be 2 times 3 times the square root of 5 minus the square root of 5. Notice that the 2 times 3 can be multiplied together and give me a 6 square root of 5 minus the square root of 5. So what this means is, this means there are 6 square root of 5's present, and I'm losing a square root of 5. Well, if I have 6 square root of 5's and I lose the square root of 5, because remember there's like a 1 here, we just don't put it there. So if I have 6 and I lose 1, that leaves me with 5 square root of 5. So the 6 is like treating it like a coefficient, and this is like the variable. So these are like what we call like terms, and with like terms, you just focus on these numbers out here. And that leaves me then 5 square root of 5 as a simplified radical. So that's kind of what we're doing here. So if we have what's called like radicals, we can combine them together. But combining them together, notice that the radical part does not change, only what we are doing on the outside. So notice how I interpret this. This means there's 6 radical 5's present, and we're losing 1. That means there's 5 radical 5's present. So that's what we mean by simplifying, just cleaning it up. If I want to get the answer, I'd have to put that into a calculator, and it would turn it into some type of decimal. So since the radical remains in the problem, I can't get rid of that radical because this is not a perfect square. This is described as an irrational number. So this is considered an irrational number. It's not gonna, the radical cannot be taken out without changing it to a decimal.